in this video, I'm going to talk about two variance estimators. The first of which is our sample variance, which is, as we know, xi x bar square. This factor is 1 over n minus 1. And we had previously defined, and we named this as variance estimator, as sometimes naive variance estimator, but basically it was the only difference that we divided here 1 by n instead of n minus 1. Now here, let me make it a little bit more formal. I'm going to call this variance, sample variance with the factor with the denominator n minus 1. So this is going to be defined as the very same formula. And I'm going to be using this one as 1 over n with I from n xi x bar. So it's the very same thing, but I'm going to use this notation, and I'm going to use the nomenclature or the phrase that this is going to be, both of them are going to be sample variance, but this is going to be sample variance n minus 1 with subscript n minus 1, which is what we call sample variance, and the one with n is the one which we do not use. There is 1 over n here. The reasoning is very simple. In the previous chapter, we have shown that this is an unbiased estimate for population variance, whereas this is a biased estimate for population variance. Yeah, it is actually very simple. You can obtain this value using this one. Actually, the reason is that the relation between those two is s minus 1 square is going to be equal to, when you multiply it by n minus 1 and divide by n, you obtain sn square. And when you take the expected values of both sides, right, I take the expected value here and here. When you do that, you are going to, well, it's going to be, this term will go out, and this expected value of Sn going to be equal to variance. Therefore, you get this relation. So this is the reason why we use this as the sample variance, right? The denominator is n minus 1. That's great. However, actually, we have skipped some point there. And that point is an important point, because we said that we decide on which estimator to use based on their efficiency. And efficiency is based on the mean square error of an estimator. The smaller mean square means a more efficient estimator. And mean square error is composed of a bias square term, but also a variance term, right? So actually here we have only talked about bias of these two estimators. Here I'm going to also talk about the variance of these estimators. The reason why we skipped that, we didn't learn a method to determine the variance of these estimators, because actually we didn't know about the distribution of these estimators here. Now we know what their distributions are. Their distributions are chi-square distribution. So actually, let's recall what chi-square distribution is. We define the chi-square random variable x square, which is equal to n minus 1 times Sn square. Note that in the lecture we simply said s square, which denotes the sample variance, but now I denote unvariance, or this Sn minus 1 to denote the sample variance here, divided by population variance. And we have seen in the lecture that this expected value of this chi-square random variable is equal to n minus 1, and variance of the chi-square random variable is going to be equal to 2 times n minus 1. So now let's derive the variance of both of these estimators. Now, if we write this as leaving Sn minus 1 here on one side, it's going to be equal to population variance divided by n minus 1 x square. So actually, just to see that we are on the right track, if you take the expected value of both sides, it's going to be, now this is a constant value. When you take the expected value, it's going to be outside the expected value, it's going to be x square. And if you put here, instead of this x square, this value n minus 1, the result is going to be sigma square over n minus 1 times n minus 1. These will cancel, and we actually again show that expected value of our sample variance is going to be equal to population variance. That's great. Now let's derive the variance of this component. This is going to be equal to variance of this whole. Now let me write the whole, all of the terms here, x squared. Note that this is a constant, so in variance operator, it's just like c times x squared. So we are going to take this out as square term. So this is going to be sigma to the power 4 n minus 1 square. And this is going to be variance x squared. Instead of variance x squared here, what we do is we use this relation here, and we end up with sigma to the power 4 divided by n minus 1 times 2 times n, I think there's a square here, yeah. 2 times n minus 1. And if we simplify this, it's going to be equal to the power 4 to n minus 1. All right. Now we have the variance for our sample variance estimator. Now we are going to do the very same thing for the other estimator, Sn square. So variance of Sn square is going to be equal to, note that we have already derived the relation between those two here in this part. So Sn square is going to be equal to, instead of that, I'm going to be writing variance of, instead of Sn square, I'm going to be writing n minus 1 over n Sn minus 1 square. And this is going to be, again, we can take this out, it's going to be n minus 1 square over n square variance of Sn minus 1 square, which is actually, we have this term here, right? Or actually this term here, let's make it even simpler. We can put it all here, and the result is going to be n minus 1 square, n square times 2 times sigma to the power 4 n minus 1. Now, just by looking at these relations, note that this is going to be smaller than 1. Why? Because this is basically equal to n minus 1 over n square. Since n is the sample size, and well, unless n is equal to 1, actually, then of course, it's for a single observation, a sample consisting of single observation, we are not going to have a sample variance because there's not going to be a variance. So n should be greater than 1, n should be at least 2. So when n is equal to 2, this number is going to be smaller than 1. So therefore, let's say for n greater than 1, therefore variance of Sn square at this step is smaller than variance of Sn minus 1 square. And let's also finish this derivation. This is going to be equal to n minus 1. Oh, let's leave it like this. See whether this is going to be easier to derive. We're going to look at that in a couple of minutes. So this is the relation that we have obtained. So let's go back to this mean square error. The mean square error for Sn minus 1 is going to be equal to, note that bias of Sn minus 1 is equal to 0. It's going to be simply equal to variance of Sn minus 1 square, which is actually equal to, let's write the whole thing here. It's going to be 2 sigma to the power 4 n minus 1. Whereas mean square error of Sn is what we call as naive sample variance, is going to be equal to bias square of Sn plus variance of Sn square. Now note that bias is not equal to 0. Why? Actually, as you can see here, expected value of Sn square is not equal to this. So let's find the bias. Bias of Sn is going to be equal to n minus 1 over n sigma square minus sigma square. So it's going to be n minus 1 over n minus 1. Sigma square is going to be equal to Have I done it correctly? Yes, minus 1 over n sigma square, if I've done it correctly. Yes, it seems to be. So we are going to take the square of this term. This is going to be the bias. We need the bias square term. So it's going to be 1 over n square sigma to the power 4 here. And this term is also equal to, let's see what this term is, n minus 1 to 2 here, sigma to the power 4 over n minus 1 here, and n square. Now maybe we can get rid of this, shall I? Yes, I think we should do. I don't think it's going to make anything easier. So this part is going to be equal to, into the common parenthesis of sigma for 1n square, it is 2n minus 2n square sigma to the power 4. And if we continue, this is going to be equal to 2n minus 1 over n square sigma to the power 4. Actually, let's take into the common parenthesis of 2 is going to be 1 over 2 over n square sigma to the power 4. Now, this is the mean square error of Sn. And mean square error of Sn minus 1 estimator is this one. The question is, which one is greater? By the way, this is n minus 1, although it looks like. So the question is 2 sigma to the power 4 n minus 1. Is this, for instance, let's assume that this is greater than 2n minus 1 over n square sigma to the power 4. Let's assume that this is the case, and if this comes out to be correct, then the first estimator Sn is a better estimator than vice versa. So these will cancel, and we cancel the values of 2. Then what do we have here? If you put n square here, n square is greater than n minus 1 times n1 minus over 2. Maybe there's an easier way of dealing with that, but my mathematics has been always awful. So this is going to be n square minus 3 over 2n plus 1 over 2 greater n squared. These will be equal to 0. Then if you put to the other side, this term is greater than 1 over 2, and n is going to be greater than 1 over 3. As we have assumed above, actually we take only consider the case for when n is greater than 1, or even if you include 1, that stands for variance. So practically we should be interested in these values. So therefore this is true. Hence this statement is true. Hence mean square error of Sn minus 1 is greater than mean square error of Sn for actually finite values of n values greater than 1 over 3, which practically means n is greater than 1. And this means that Sn, let me write it again to remind you what we have here, is equal to 1 over n from I1 to n xi by x bar square. Although this is a biased estimator for sigma square, and although Sn minus 1 is equal to 1 n minus 1 from I1 to n xi minus x bar square is an unbiased estimator for sigma square, Sn has a higher efficiency compared to Sn minus 1. That's an interesting thing. So actually there may be a reason why a biased estimator may be used instead of an unbiased one, because this has a higher efficiency. Why does it have a higher efficiency? Because it has such a lower variance, so that not only it counteracts the variance, or it is much smaller than the variance of Sn minus 1. Even if you include the squared bias term on its variance, still the variance of sample variance is going to be higher compared to this variance estimator. So that's all.